Alright, hello everyone. We're going to do a practice problem. Again, this is one of my first videos with writing it on the notepad like this, so we'll see how it goes. If you have any questions or comments or concerns, just let me know, and I'll try and make changes accordingly. This is problem 1882 out of the textbook. It talks about acetic salicylic acid, which is aspirin. There we go. So common aspirin, it has a Ka in the body, so body temperature is 37 degrees. That means Ka is going to be a little bit higher than what it normally is. Body temperature at 37 degrees Celsius. Ka is 3.6 times 10 to the negative fourth. It tells us the initial concentration of aspirin, which is HC9H7O4. The initial concentration was 0.018 molar. And it wants us to figure out what the pH is. So let's take a look at the structure really quick, because this is what we're going to be talking about later on when we start talking about structure versus acidity. There are a couple different hydrogens labeled here. I have these hydrogens selected, or there's that hydrogen, or there's these hydrogens out here on carbon. Now it turns out that this one over on the oxygen, that's going to be our acidic proton. So that's the one that's going to be leaving. That'll leave a negative charge on that oxygen there, and that's going to be our product in this case. The reason that that one's the acidic hydrogen is because that's connected to an electronegative atom, and that's going to polarize that bond between oxygen and hydrogen. So that bond between that oxygen and hydrogen gets polarized, and it makes it easier for that bond to break and this hydrogen to be donated to another compound. So in this case, it would be this hydrogen gets donated to water, and we form H3O+, and we're left with that negative charge on the oxygen there. These hydrogens out here on the carbon atom, so these are all carbon atoms in the middle with those double bonds. These hydrogens are not polarized enough, so they will not leave. Same thing with these hydrogens here. They're connected to carbon. They're just not polar enough. They cannot be donated, at least not in water. It's not strong enough. So we go through to solve this one. Again, we're asked for pH, and since this is a weak acid, we can see it's a weak acid because Ka is less than 1. It's a small number, and it's not one of the 6 or 5 strong acids I asked you to memorize. We can go through and begin writing our weak acid equilibrium. So we have HC9H7O4. We're going to make this aqueous, and we're going to dissociate it into water, and we set up our weak acid equilibrium. We will get C9H7O4 minus, and our other product, H3O+. So here's our reaction. We're in our initial concentrations, our change, and our equilibrium. And let's see if I can get this quickly here. Draw a line across there, make it look kind of level. There we go. Ooh, this is going to be a lot better than class. All right. So now back to drawing. Uh-oh. Maybe not. All right. So our initial concentration was 0.018. The water we don't have to worry about. These are both 0. Now remember, H3O+ is not really 0, but it's really, really small, so it doesn't matter. The reaction is going to go to the right, where we lose X from both sides, or we lose X from the left side and we gain X on the right. So now we have 0.018 minus X, and we're gaining X on the right. So that's our equilibrium condition. We always ask ourselves, what is Ka? So let's write our equilibrium expression over here. Ka is going to be the ratio of the products over reactants. In this case, the product is H3O+ and C9H7O4 minus, and that's all over the initial HC9H7O4, our initial reactant. And again, if you would like, you can always, for that acid right there, you can always just write HA, and this would be A minus. That's always acceptable as well if you want to save yourself some time. So we know that Ka is 3.6 times 10 to the negative fourth, and that's going to be equal to, in this case, it's X times X over 0.018 minus X, and we're just going to go ahead and assume that X is small relative to the actual initial concentration, and we get to do that for any weak acid problem. For most weak acids, we're just going to assume X is small and plug right on ahead. It's going to make life a lot easier. So now we have 3.6 times 10 to the negative fourth is equal to X squared over 0.018. And I'll bring this down over here. So, let's see if I can get fancy here. I'll move that over here. Hey, look at that. And I didn't move it down far enough, so it'll be fine. So I'm going to multiply both sides by 0.018. And I end up with, checking my notes, 6.48 times 10 to the negative 6th is equal to x squared. And we just simply take the square root of both of these. And you end up with x is equal to 2.55 times 10 to the negative 3rd. Alright. Now remember, in this case, x represents the concentration of H3O plus, and, well, let's change that. And it equals the concentration of the C9H7O4 minus. Should have started with HA and A minus. But in this case, since we want the pH, we're just going to need the H3O plus. So we're going to say pH is equal to the negative log of the concentration of H3O plus. So in this case, our pH is equal to negative log of 2.55 times 10 to the negative 3rd. You just crunch this number out, you get pH is equal to 2.6. So there's an important point I want to make here about significant figures. If we look here in a log term, we have 2 decimal places in the number. If we write the number in scientific notation, we see we have 2 places past the decimal. So we have 2 decimal places in the log term, which means we get 2 sig figs in the final answer. So that's why I'm shortening it off to just 1 place past the decimal, because 2 decimal places in the log term means that we get 1 sig fig or 2 sig figs in the full answer, or 1 decimal place. Hopefully that went well. We'll be doing more problems like this, and you'll be able to review and follow along. You get to play this over and over as many times as you'd like. Let me know if you have any questions. I'll keep working on problems like this and sending them out.